PETSc. Sorry, I'm writing people emails about Phoenix. Don't use Phoenix. No one use Phoenix for anything. Wrong one. I think that's now on the recording as well. HDMI, sorry. Wrong button. VGA, short.
That should be it. Should I try to reconnect?
I guess.
What is going on? Let's try. This instead. Interesting. It was working. No why. Does this think there's an external monitor?
Yep.
This isn't completely crashed. So that works somewhat. No, it doesn't. Wait, it does. Okay, so that bit works. There we go.
Okay, good morning. Thank you for this nice opportunity to present my work here. And as you said, I'm Vaclav Hapla and currently working at ETH at the Department of Earth Sciences. And I will start with a small simulation already. Can you see the difference here and here? So that's how I saw the first day here, because I forgot my clear glasses at home in Zurich. So this was my view, and I rather chose this one, wearing sunglasses with prescription. So I fortunately had this, but it's kind of dark. But fortunately, opticians here in London made great work, and in less than 2 days I had new clear glasses. So thank you. And I will start with a very personal view of PETSc. How I started with PETSc was in 2010, and I was writing down the thesis quite late, and PETSc was proposed as one of the tools. And I had a very limited experience, so I compiled it on Windows, and right from the beginning with the MATLAB interface. So, and I also somehow insisted on Visual Studio, so it took me really 3 days and nights of compilation, but at the end, the playing with the PETSc API was just a sweet award. And then during my PhD studies, I co-founded a project called Permon. Jakub Kružík was already talking about that, so it's a mainly quadratic programming framework, kind of flawless extension of PETSc, so something like SLAPC. And we introduced their concept of QP problems, transform and solvers. and some concrete solvers, mainly augmented Lagrangian one and active set algorithms. And also on top of that, there is a implementation of fatty domain decomposition with constraints, thanks to the quadratic programming infrastructure. So with this, you can solve some large-scale contact problems, for example. And more recently, we also started so-called Permon SVM, which is a module for machine learning using support vector machines. And these packages are using FreeBSD license, and I, of course, opted out from the development because of going to ETH, so I'm not working on that at the moment, but fortunately, my young colleagues took over and they continue, and finally we will find some nice synergy in the near future. Interestingly, I also started to give some PETSc courses quite soon. It was kind of in Czechia, we became members of so-called PRAISE, which is a partnership for advanced computing in Europe, and we needed to contribute something to the training activities. So I was asked, like, Vaclav, you know something about PETSc, you could maybe give tutorial about that. So I started like in 2012, was my first bigger tutorial about PETSc in Krakow in Poland. And then I also co-organized PRAISE Summer School in Ostrava, in our city. I invited personally Jet Brown and Nick Oschlemer for that. And then also some schools in Linz and so on. And it was kind of more introductory tutorials, majority of time spent in hands-ons, and even training in Linux command line and Git, so for very newbies. And how I got to ETH and geoscience in general, thanks to PETSc. So my current colleague, Mike Afanasiev, sent a position offer to PETSc Dev mailing list. So it's, in fact, completely public information how I got there. You can still find it in the mailing list archives. And I immediately forwarded this opportunity to my wife, and we decided very quickly to apply. So, in short, it took less than a month before I say I take it, and I started in September last year. So this is my current group, Seismology and Wave Physics. Swiss-like hierarchies, so this is the hierarchy. And this is my current professor, Andreas Wickner, very nice guy. And our topics in the group are like seismic tomography, noise interferometry, and interestingly also medical imaging, concretely ultrasound tomography. And I will talk also about this stuff. And this is my funding, basically, so-called PETSc. So this is the Swiss platform for advanced scientific computing. So it's basically an initiative to support high-performance computing in Switzerland. And two main activities are PETSc projects, so this is also my funding, and annual PETSc conferences. So next one will be at the beginning of July in Basel, in Switzerland. Here you can see it was a quite complicated process to get there. I have already 2 children, this little mouse and cat. You can distinguish based on the shape of the ears. And now about the work itself. So the main topic why I came there is this full waveform inversion across scales with Salvus. So what is Salvus? It's a software package for full waveform inversion across scales. So it started mainly with seismology stuff, but also what is interesting for industry is non-destructive testing using ultrasound and medical imaging. So it's a software suite designed for large-scale full waveform modeling, forward modeling and inversion. For forward problems, it uses spectral element method and of course full waveform inversion using adjoints and nonlinear optimization methods. Focus is on both flexibility and performance, and it's a modular set of packages. So there is also standalone measure tool and workflow tool, and it's all written in C++ using template mixins and dependencies of PETSc and Eigen. So as I said, for the forward modeling, we use spectral element method. So it's basically a finite element method with high order shape functions and particular quadrature rules. So the shape functions are high order piecewise polynomials. We make use of tensor product Lagrange interpolons within each element, and nodes are placed at the zero of the polynomials. And this is combined with Gauss-Lobat quadrature. So quadrature points coincide with the nodal points, and we can take advantage of fast tensor product techniques. So it's basically the same as Luana was talking about yesterday. So some computational consequences of this choice is that there are relatively large number of degrees of freedom per element, even hundreds, and we use fewer elements to attain the same accuracy. So it's good for modeling some rapidly oscillating phenomena like turbulences and waves. The mass matrix we get is diagonal, so it's trivial to invert. And as Luana was saying yesterday, it's we have to use matrix-free stiffness matrix, so using math shell.
Using an explicit time-slot movement?
And to apply this matrix-free stiffness matrix, we use Eigen. So Luana was talking about directly using blast routines, we use Eigen.
So we use explicit or implicit instead?
I think explicit.
Explicit. So the stiffness mass matrix is for what? For the backward problem?
Yeah, it's only at the end of the time step. It's not applied in the iterations. Yeah. So the architecture, as I said, is using template mixins. This is something, I mean, similar to, for example, DL2, but in this case, it's optimized for waveform inversion, particularly in seismology. So you can combine your different shapes of finite elements, different equations, different physics, different boundary conditions, and I/O like Lego bricks, basically. And how is PETSc used in Salvus? So there's mainly heavy use of the DMPlex stuff with kind of additional multiphysics support, and then only some utilities. So as I said, the resulting system includes only mass matrix, which is diagonal, and the guys decided not to use PETSc for some reason for the solution. So, yeah. But currently, there are some first experiments with tidal loading, which is also these animations, and this is already more interesting from the numerics point of view, because it requires linear system solve wave stiffness matrix. So this is from a prototype which uses KSP and the mud shell operator and diagonal preconditioner. In Outlook, we want to implement a completely standalone package for Helmholtz stuff. So mainly for frequency domain wave equations, which will be more interesting for me regarding the use of numeric stuff in PETSc. But we have to analyze what was the best solution. I would be really glad if we use completely the PETSc stack, including also PETSc FE. This is something about particular use of DMPlex in Salvus. What is interesting is this kind of multi-physics support. So here we have a problem where we combine elastic and acoustic elements. So this is how it looks, and how looks the mesh, and how looks the DMPlex. So we have kind of coupling edges with two different physics. And I think this is a nice example of how DMPlex is helpful, because I can't imagine how we would implement this using some normal mesh structures.
Do you have sections that only go over part of the domain for physics? Yes. Okay.
Yeah, this is another example. So how the seismic wave is propagating from the interface of water and the ground. So this is from real data from Japan Islands. And this is a nice synthetic example where we have like alternating acoustic and elastic cells. So it's nothing useful, but it shows how it's flexible and how DMPlex enables us to solve even these wild problems. And this is our current challenge. So maybe you know that there is something called NASA Inside Mission this year, and the goal is to place a highly sensitive broadband seismometer on the Mars planet. So the spaceship was already sent last month, and estimated arrival is in November. And the goal is to investigate the deep interior structure of Mars. So the elastic wave propagation are crucial to interpret the data from the seismometer, and at the highest frequencies the resulting system can have up to trillions of spatial dots and hundreds of thousands of time steps. So it's a pretty challenging problem. We can take advantage of wave equation reciprocities, because the receiver is in fact only one, but the number of sources is much bigger, so we kind of swap the roles of these two. And this is an animation of hypothetical earthquake on Mars, which is used to show that we are able to solve these kind of problems. So here are some facts about this simulation. So as I said, it's a hypothetical Mars earthquake that can be exported by one seismometer. Once it is deployed there, 3D cross and topography effects are taken into account. So far, it's only 6 million of elements and 300,000 time steps. And this already results in 10 tera degrees of freedoms. So this was calculated on 7,200 cores of case-dained machine, almost in real time. So, but this visualization is fancy, but in fact, to do some science, we will need much more data, so much finer resolution, and the mesh sizes should be like up to 50,000 times bigger, which also, because of the high frequencies we want to simulate.
What polynomial degree are you using here?
Sorry?
The polynomial degree. What polynomial degree are you using for this simulation? You have 6 million elements, but the degrees of approximation is how much? 7,
I think several times. But
the polynomial degree of this simulation.
Oh, polynomial degree. You guys do like at least 5, right?
5.
It's in the paper.
yeah,
Okay.
yeah. In fact, you know, to be honest, I was not running this simulation, but I can ask if you are interested.
The examples that Mike showed last time in your talk were 5.
Okay.
So when you're counting your degrees of freedom, is that including all of the time slices? That 6.5 million elements times the number of degrees of freedom times 300,000 time steps?
I think so.
Okay, this is just a forward simulation, right? This isn't that.
Oh no, it's already actually.
Okay, that's already it.
Yeah.
Yeah, that's, you're right.
Yes. So this is the seismometer, and this is what we get from the inversion. So interestingly, this movie was part of official NASA press materials during the mission launch broadcast, and it was in fact the only material from outside NASA. But as I said, we want to solve even much bigger problems, and here we face a bottleneck kind of in the mesh I/O, and this is in fact stuff I was working on so far. So the current state is in PETSc there is kind of asymmetry of input and output formats. You have much more input than output formats there. Only HDF5 can be used for both input and output, as far as I know, and only MAT format can be loaded in parallel. Other formats are just loaded onto rank 0. And in Salvus, we were stuck to Exodus format, so using DMPlex create Exodus from file. And the model data are loaded in a custom way from Exodus. So if you look how the HDF5 I/O works in PETSc, the state was that mesh dump into HDF5 is stored with two like redundant topologies. One is kind of DMPlex serialization, and one is the one compatible with the XDMF format, which can be visualized in ParaView. The Exodus loader is sequential, and this is already becoming a bottleneck. Because, as I said, you have to load the whole mesh onto rank 0 and then scatter the mesh across all processes. So there was a need for a new format. And here are some selected requirements we wrote down. So, of course, parallel I/O. We thought that it could be a good idea to base it on HDF5 because it's an open standard. It's kind of documented, uses MPI I/O, and it's kind of flexible. And we also need to specify material parameters per element, node, or integration points. Something equivalent to Exodus site sets. And if possible, have the same format for input and output, which would allow some flexible workflows, such as here, produce mesh, partition, enhance the mesh, save mesh, then visualize, maybe even do some manual edits afterwards and use as input again. And we wanted to separate the mesh topology from the geometry. So my idea was to use XDMF, which separates light and heavy data. Heavy data are in binary HDF5, and the light data are like metadata in XML, which specify number, times, precisions, locations, dimensions, and so on. And it kind of gives meaning to the raw data chunks in the HDF5 file. So this is stored using XML, and it's both machine and human readable. But there is, in fact, some current support for XDMF in PETSc. Just the PETSc and visualization topology are two different things. There is already a sequential HDF5 reader and parallel HDF5 writer. XDMF file can be produced like after the PETSc app run using provided Python script. It's kind of only one way. It's meant just for the ParaView visualization. So we decided, instead of implementing some completely new format or so, to grasp this XDMF, but improve the support in PETSc. So this has some advantages for me, like it's for me easier to defend funding, and it's also something that could help the whole community. Even some other FEMCOs could grasp XDMF as their kind of native format. And I took Salvus only as an example of such a package. And these requirements I was talking about are basically met with this format. It's all like implicitly met. Only the Exodus site sets is more interesting, but it can be modeled in XDMF using set and attribute elements. And the good thing is that it's applicable actually to nodes, edges, faces, and cells, which we need. This mechanism is even able to store any DM label, I would say. There are also some pitfalls, like it's definitely not a replacement for PETSc native HDF5, because XDMF still has a limited set of element shapes. Also, of course, it's always tricky to model mixed cell shapes, but XDMF actually supports it by using multiple topologies or one topology of the topology type mixed, where you can combine really different types of elements in one topology. And we will also, of course, need some custom additions, but both HDF5 and XDMF allows that. In XDMF you have something called information where you can store everything you need. And there is, of course, also some criticism of HDF5. It's not that stable, it does not evolve that quickly, and so on. We had some discussions already about some new format, but I mean, at the moment there is no widely used alternative to HDF5. So I started with a parallel HDF5 reader, which is already in master of PETSc. It's kind of simple. We just load the disjoint portions of the mesh directly onto different ranks. PETSc has a nice HDF5 interface already for loading vectors and index sets. And by this means we get some naive partition, which is constructed in a DMPlex way using DMPlex create from cell list parallel function. And then you can redistribute this naively partitioned mesh using some parallel partitioner. For example, Parmetis or PETSc. There is again some discussion now about the available parallel partitioners, but these two guys are the most widely used. But I will definitely do some experiments also with other partitioners. And I connected with that is that I introduced new PETSc viewer formats. So now in master you have PETSc viewer HDF5 XDMF, so it's just the data which are actually required from the XDMF, like the minimal data that describe the mesh. Slightly different is HDF5 WIS, which is the same plus some specific data for paraview visualization, as I get it. For example, some cuts. HDF5 PETSc is just the DMPlex serialization, and PETSc viewer default or native, it's like how it behaved before. So it's all together in one HDF5 file. So there are still some to-dos. I would like to implement actual XDMF file output. There is some C++ API for that, or I can use some general purpose XML API, or just plain ASCII output. I still have to think about it and compare these approaches. And I also have to implement phase sets and other labels using attribute, as I said, and somehow implement also the storage of the integration points, which is of course not directly supported, but there are some ways, like you can, for example, assign attributes of the vector type, so there are multiple attributes per one node, for example, so it's doable, I mean. So this is gonna my personal summer of code to implement this stuff this summer. Okay, so that was about Salvus, and now something completely different. That's another interesting topic. I started like only 2 months ago or so. So I became a part of a project which tries to improve the breast cancer detection using ultrasound. What was the time, please?
It's now, you've got about 7 minutes.
10 minutes?
7 minutes.
7 minutes. Okay. So I have to be quick. So the breast cancer, of course, quite common lifestyle disease, the more so in Western countries, you can say. And I wasn't surprised that it even exists among men, which is like 1% of the cases. So like the state-of-the-art, what is currently used is the X-ray mammography, which brings some risks because of the pressure and radiation. So this diagnostics is itself among risk factors, which is not nice. And there are also problems with dense tissue, which is the case typically among young women. So this is one of the reasons why the regular screening starts only at the age of 40 or later. And also insufficient specificity, you cannot basically too much distinguish, for example, between benign and malign carcinomas. So current effort is to use some more advanced ultrasound devices for that, where you use ultrasound waves as physical phenomena for imaging. So you can make use of multiple information such as sound speed, attenuation, reflectivity, and others, and also model both transmitted and reflected waves. It has much better resolution and contrast than the normal mammography, and it's also much more comfortable for the woman. She just lies on this device and breathes this in the water. So it's completely radiation and compression free, and it's also more objective because like the position of the breast is kind of defined, and it's able to classify tissues and distinguish between benign and malign. And not exactly this device, but something similar is already in clinical evaluation. And classical methods to deal with the data are using, for example, inverse radon transform. But from seismicity, so from the stuff Salvus is doing, comes the approach using wave equation inversion, which is still under academic research. What is interesting that these two problems have kind of similar characteristics, similar scales. You just kind of replace kilometers by millimeters, and it's almost the same. Even the number of wavelengths in target, so also the complexity is similar. And the main challenge is find some trade-off between accuracy and computational cost, because full waveform inversion is of course the most accurate approach, but it produces really big problems. But the current devices use mainly high frequencies, so the systems are even bigger, and we need short time steps and small cell size. Such big problems are of course solvable on big clusters, but it's an issue in hospitals to send the data to some supercomputer. They tend to use rather dedicated workstations. So, because, for example, wall time on big clusters is short, but time to start can be quite long because you wait in the queue, for example. But mainly the legal issues, you know, all these emails about GDPR now. So you can imagine. So there are several combinations, but the top combination and the bottom combination are currently not doable. The one on top, like using ray-based approach and 2D using superposition of slices, it's not accurate enough. Whereas here, full waveform inversion plus 3D imaging, it's the best accuracy, but it's not doable on such workstations. So different trade-offs are used. Some groups use full waveform inversion plus 2D, which, for example, introduces some artifacts. So we currently stick to this one. So ray-based plus 3D. I will go through quickly. It's basically a very simple problem, a straight approach. You basically integrate numerically it's kind of ray tracing, so you integrate the slowness across the ray. And the result is a rectangular system. It can be both underdetermined or overdetermined based on the configuration. And the resulting problem is, of course, totally ill-posed, so some kind of regularization is needed. The simple one is Tikhonov type, using finite difference Laplace operator. But the better thing is to use total variation regularization, so you kind of minimize simultaneously the rate it varies. This stuff is to be implemented. We just use some sequential C implementation for now. And other regularization should be studied also. And current effort is to make the trade-off easier, something between straight array and full waveform inversion. So this is what my colleague Nayara modeled like last week. So we call it travel time waveform inversion in contrast to travel time straight array inversion or full waveform inversion. So it's already a wave equation, but not full waveform, basically. The result is still a linear problem. Of course, the matrix is much more populated by non-zeros, but the solver code can be reused. And nice thing is that we have the way to control the trade-off using sensitivity between source and receivers. So you can like model everything between full waveform and straight array. So this accounts for finite frequency effects and also allows 3D reconstruction, which is the case on this picture. So now we have this slider here, which allows us much better flexibility. And that's basically it. There are also some potential future projects in our group. For example, there are two master students which are finishing now, and they both do kind of numerics. So I'm really looking forward to work with them. And that's it. Thanks.
Questions? Matt.
So you have the slider on the left side where you're kind of saying that you have an intermediate model between SWI and just the high frequency clustering. But do you think there's any hope on the right hand side for like things like aggressive mesh editing? In particular, mesh editing is driven by the sensitivity to your output functional rather than accuracy of your base.
I think so. It could be interesting.
Jared.
Yep.
For this network problem, do you have a high number of sources?
Yes, that's the basic difference. In fact, that you have much more. You have, for example, 100 of Yarkov transducers. So they are, I mean, sources and receivers at the same time. And it's nicely.
But like, I guess that's the follow-up question then is connected. So
Uh-huh.
in that sense then, the other way that you can make this computation feasible is just by exploiting the trivial parallel nature of that, because you can execute, if you're doing your path propagation, it's a map reduction, right?
Uh-huh.
Map reduce operation where you can run all sources simultaneously.
Yeah.
And
So
propagation and reduction.
I should add that there is like always one source, and all other act as receivers, and they are like sequentially altering these sources. So it, like in this picture, literally.
So if you're going to have 2D regularization, and you put in something like regularization or the plentiful shrink operator, so where does that go? Is it like,
I want to implement it in PETSc directly.
you already put it where? SNES?
Oh no, TAO I would say. definitely. Because it's kind of special constraint, right?
Well, I was interpreting it as the solver for a trivial non-smooth problem. You just kind of solve the outline part, plunk down to the rate. So in my mind, it was like a SNES type thing where that only works well for one particular equation.
I would say that if it is implemented in general way, it's kind of useful for any rectangular system, basically. Yeah.
Okay, so we should wind up there. Thank you very much again.
Thank you.
Let me just kill the recording.